Our next speaker, I would say he needs no introduction, but there may be a few folks been living under a rock and don't know who Chris Rowen is. But I've heard his name for quite a while. A lot of us have been pretty envious of how smart he is and how much he's invented, started companies. He started Tensilica. Before that, he was instrumental in starting MIPS. So he's had some major efforts and was involved early on in developing a RISC processors. His background, bachelor's at Harvard, master's and PhD from Stanford. He has all the credentials, but not just that. He has the expertise and delivery that show he's somebody you need to listen to today. And so it sounds like he's still having fun, even though Cadence acquired his company, and it sounds like that's opened up more opportunities. And so welcome, Chris.
Thanks, John. I'm not sure I can live up to that introduction, but that's very kind. My goal today is to talk a bit about the power issues around IP. And of course, I'll touch a little bit on tools, but this is not fundamentally a tools talk so much as it is giving some glimpses into some of the high-level issues and some of the specific methods that we have used to get our arms around power as we build a very substantial IP business. I think we should start with some kind of high-level assessment of what are the issues, starting from, well, why do you buy IP, and what is the role that energy plays in system architecture? Because ultimately, we don't do all these beautiful chips for their own sake, but because they're hopefully solving somebody's system-level issue. And I think the issues around power are really quality issues. And it really reflects the fact that our definition of quality is expanding from something that was largely focused once upon a time on functionality, and now is bringing many more dimensions of performance and power and robustness. It's quite clear that power in general is a function of many things, but particularly when you talk about IP, you're not just talking about some physics level assessment. This is not just working at the level of CV squared F. You really have to think at the level of what is the application I'm trying to accomplish, or what is the suite of different applications that I may need to cover with this particular design. And so the issues of workload, configuration, tool measures, and design methods all kind of come together to give us an equation which is, of course, built in some deep sense on CV squared F, but really is a different kind of dialogue. From there, I can talk a little bit about some of the tools issues, some of the traditional challenges there, and some of the questions of what happens as you deal simultaneously with digital and analog. And then I'll spend really some more time talking about IP, talking about the issues of optimizing energy and power in processors. What's the relationship between visibility and control and the quality of results you get from a power standpoint? And go into some interesting little tangents on voltage scaling and mixed signal. So I think it goes without saying that third-party IP is an important element of the ecosystem in which design takes place. And I think it reflects both the absolute complexity of the chips that we're designing and a shift of focus of people who are doing SoC designs that are of necessity a little bit less focused on the low-level details of every transistor and every wire, and much more about, well, what is the system-level function that they need to do? In that sense, every chip design company is becoming a system design company. And if they are becoming system design companies, then they need someone else, in many cases a third-party provider, to worry the details, to sweat the issues of correctness and availability and standards compliance and power on their behalf for the building blocks, which are now growing into the hundreds per chip. And that's fundamentally what drives the economics and the technology of the IP business. In the case of Cadence, we have chosen to focus in some areas and chosen not to play in some other areas. And these are quite conscious choices about what we are trying to do here. Whoops. I had thought that was a laser pointer, but it's a backward button. So we've really focused a lot on the interfaces, the things that drive significant streams of data in and out of memory and in and out of the popular high bandwidth I/O interfaces, whether it's Ethernet or PCIe or various flavors of USB, and in and out of memories of all kinds, and the data-intensive computational problems, the deeply embedded control, and especially DSP. These are the blue-collar computational problems, usually complementary to what's happening over there in the applications processor, which is running high-level software and is often in the business of delegating the heavy lifting, what's happening at the pixel level or at the sample level, at the bit level, to different kinds of computational engines. And we also don't play in the on-chip memory library, standard cell library space, because there are plenty of suppliers there. But these high bandwidth, high sophistication, high compute elements are very often the defining characteristics, and they represent the great bulk of the power which is being dissipated in many of these chips. And so it really is important to have a handle around those things. So what you find as you start getting into this kind of a business is that there are some old models of what the IP business was about. Now, once upon a time, and I remember this very clearly, you could easily characterize the IP business as the IP flea market. That is, there were lots of little shops, people had done some piece of design, dusted it off, and called it IP, and prayed that someone would just stumble across it in the dark somehow, and money would fall out of their wallet. And then some poor sap in engineering was going to have to take that dusty old piece of IP and find a way to incorporate it. I think there's been a more modern, but still rather old-fashioned notion, which you might call the IP warehouse, which sort of says, well, you know, it's there. I don't know what it is, but, you know, it's got a price on it, a label on it, and we know how to stock it. It's prepackaged. It tends to be not very flexible, not very customizable. It is what it is. I think increasingly, because of the demands of the applications, that this model in which, you know, you really are much more built to order, much more built to integrate, much more customizable, configurable, programmable, and much more driven by the end application, has changed significantly the types of IP that people can make money at, the types of IP that can be simultaneously standards-oriented, easily understood, and at the same time lending to increased differentiation for the product that they go into. So let's now shift from that picture of the nature of IP to the nature of system architecture. And one of the things that's really important to understand when you're talking about power in IP is thinking about the power and energy of the total system. And there are many, many different kinds of transactions that you can think that an electronic design is doing. From the lowest level transaction, you might have the switching of a single gate or a single transistor, to, at the other end of the spectrum, an HTTP transaction with a Google server 1,000 kilometers away. And you actually can do an energy estimate for this, and you can find a characteristic physical scale associated with it. And we did a little bit of work to sort of say, okay, well, what does that look like? And on this log-log scale, it's actually kind of linear, which means that over an enormous dynamic range, you're going from something where you can say, okay, the relevant physical dimension of my subsystem is 16 nanometers, and you're dissipating maybe something on the order of 10 to the minus 14th, 10 to the minus 13th joules per 64 bits, to something at the other end of the spectrum when you say, I'm sitting at my IoT device or my phone and I'm doing some transaction with the Google Cloud, and that's on the order of a millijoule, so a mere 10 orders of magnitude more energy, and similarly about 10, 11 orders of magnitude difference in physical dimension. And so what this really means is that we're going to have hierarchies. We're going to have distributed computation. We're going to try and do as much locally as we reasonably can, because moving a computation from something that has to go over 1,000 kilometers to something that has to go over a few microns is clearly going to save you many orders of magnitude in energy. But it is this palette of different techniques, different levels of the memory hierarchy, different usages of memory, different usages of local and remote storage, and different uses of the cloud, which really now dictates the kind of systems that we're building and the kind of trade-offs we make as architects as we work to push as many transactions locally as possible, at the same time that the nature of the modern application, in which we really do want to find ways to appropriately share and get access to the world's information, says we want the illusion that we're going to the web all the time, and we want the battery life associated with going only 16 nanometers at a time. And that tension between these two goals is the great challenge of system architecture of the current era. So what is power a function of? Well, clearly it's CV squared F, but there are a lot of other factors at work. And I'm taking one example here as just a way to motivate some of this discussion, where I just took one of our standard DSPs and looked across a range of different workloads. So these are different applications or kernels, all of them arguably intensive DSP computations. If I looked at the power, if I said, well, what happens if I'm executing some lightweight scalar code or executing no ops, I'd be down here someplace. But these are all real DSP workloads on a significant DSP, and you find that you've got a dynamic range of 2.5x, just as a function of what code you're running in the power dissipation. And moreover, you have, of course, the other variability that depending on how hard you're pushing the circuit, you're going to get synthesis and place and route, which is sizing up gates and is dissipating significantly more power as you go from a target of 200 megahertz, say, to a target of 600 megahertz. And so what you find is you have a very large space where the power is, you're trying to say, I need to accurately estimate the power right here, but am I really someplace else that's far, far away because, in fact, I'm not considering the right workload. So workload is important. I haven't even shown the impact of configuration here, but just as an example, if you take the Tensilica configurable processor family, if you compare the power per megahertz for the smallest configuration that people have put into production to the biggest one, you have between 2 and 3 orders of magnitude in milliwatts per megahertz for that core.
Chris, might be better if you use the lapel mic.
Yeah, that's a good idea. I haven't been known yet to stand in one place.
You're high energy, you like the wall.
That's the first time anybody said that. Thanks. So, you have this very large configuration space and this huge variability in the amount of power, even within what you might argue is one IP. So, if you add to that variability in the configuration space and this variability that comes just from workload and target megahertz, you now have between 3 and 4 orders of magnitude of variability, arguably, within one IP. You also have this interesting contrast where some of the things that you want to do to reduce power inevitably contribute to increasing the variability of power. So designers in general, processor generators in particular, have gotten very good at automated clock gating, data gating, looking at specific scenarios and figuring out exactly what's the minimum set of logic that has to be activated in a given scenario. But it means that you reduce significantly the power when circuits are inactive, and so you become very sensitive to the mix of circuits, the mix of instructions that may be executing in that. And to really understand what point we're operating at in the total configuration space takes a lot of work. And so it may require, again, if we take sort of the standard processor generator as one example, it takes hundreds of simulation runs on scores of different layout databases just to form a reference set of data points from which the total configuration space can be covered by interpolation and extrapolation. And so having this thorough characterization, it gives us a way to make reasonably good estimates of a much larger design space. So increasingly, I've recognized that this question of power modeling is really becoming central to the perception of quality. It used to be quality was, for an IP was, well, does it meet the standard? I mean, if you look at the waveforms, does it do what they're supposed to do? Are the ones and zeros in the right places according to the manual? But instead, it's not just about functionality. It's often about performance, in this case, perhaps throughput in application, robustness. How well does it handle static and dynamic faults of various kinds, and about power. And we find that in order to really think about this in a suitable top-down fashion, we need to have a flow that allows us to, of course, estimate the power quickly as we make changes in the design or in the configuration of the IP, to have some mechanism to support real-world workloads, to be able to handle the usage scenarios in a systematic way, to be able to get insight and to measure, visualize, to get some intuitive summary feeling about what's going on in the power so you know which parts of the problem to work on as you design the IP or as you integrate the IP. And to be able to then actually have realistic ways to reach in and change things in response to the different needs. I think that the challenges come from the fact that you have this very large space, but you still need as much accuracy as you can get. So that you do need, especially as you move to advanced nodes, to take care of all these different kinds of effects, some of them driven directly by the more and more bizarre behavior at a low level of these very large circuits. So on-chip variation and IR drop and sources of noise and all of that in the presence of aggressive schemes for voltage scaling and voltage adjustment. You need to figure out, well, where do the realistic workloads come from? This is a real challenge in a Verilog simulation-centric world because you can't just say, oh, well, my application is taking only 1 billion cycles to do something interesting. Let's just run that RTL simulation for 1 billion cycles. Not going to happen. And therefore, you have this tough choice between, do you go to very abstract models of power, or do you look at my 1 billion cycle problem 1,000 cycles at a time, which also is not very satisfying. I think that it isn't just enough to know what the power is, but you want control over it, and finding the mechanisms by which either the configurer of the IP or the designer of the IP has control over those things, including being able to get realistic real-time feedback in terms of power is difficult. And mixed signal remains a real challenge. I mean, it's already a high art to get those circuits to work in a stable fashion across all of the process corners. And power modeling is at a less sophisticated level, unless you're willing to go in and do, redo the whole SPICE simulation under all of these conditions with the target towards understanding power. So there are certainly a well-established methodology in RTL power analysis, and it's worked remarkably well, I think, in terms of giving people some rough approximations to what they'll expect to see in silicon. But they have a number of shortcomings in terms of really shortcuts that are taken in understanding all of the effects of glitch power and clock trees and the power generation and power gating structures, the impact of DFT structures and multi-VT is not fully comprehended in every flow. Some of it comes from the fact that you are made even more challenged by the fact that you cannot drive stimulus to cover the interesting power cases, in part because power is a system issue, whereas stimulus is a cycle-by-cycle issue. So you really, in a sense, are only doing one stimulus at a time. We don't have necessarily very good ways to collate, aggregate, sum up the power at an SOC level. You get very large activity files because our representations are so low level today. And it's prohibitively slow because of the simulation technologies which are available to us for accurate or reasonably accurate power. And then, if you find something that you don't like the looks of, if your number is not what you hoped for, then what? How do you go and roll back from an aggregate number to something that tells you really what part of the design was higher than expectation? How do you break it down to get some insight into what's happening? And this is made worse by the fact that in order to close timing, you tend to flatten the hierarchy, which means throw away all identity about subsystems. And then you've flattened this whole thing in order to meet timing, and then somebody says, well, how much is spent in the register file? And you go, shit, I can't even find the register file anymore. And so the environment in which we can look at the details, I think, still leaves a lot to be desired. So now let's think a little bit about what the tools can do and what's happening in the leading edge of tools. And we start from kind of this power analysis landscape where there are these chasms, where there's a set of things that we can reasonably attempt to do in system level design and verification, a set of things we can reasonably expect to do in implementation, in synthesis and place and route, and some things we can reasonably expect to do in sign-off as we do various forms of timing and power and signal integrity. But there are a nasty set of problems. I've got all these activity files from all of these different IP blocks, in-house and third-party. How can I get a real power picture of it? I've got, how do I actually deploy this information that I've now gathered on this net list in order to actually do power reduction in the implementation? And how do I actually get some interesting amount of input through it? And how do I zoom in on, for example, peak power windows so that I can figure out where did things go wrong? And, and I think there are we need more and more connectivity among these different things that brings together an understanding of the power tree and the clock tree and can create some of these connections to allow these to work together. And of course, Cadence is, I think, pushing very hard and in many ways extremely successfully in this area, whether it's bringing to bear new kinds of emulation, simulation platforms, significant improvements in the degree of visibility that are coming out of the implementation tools, whether it's synthesis or place and route, and a lot of things in terms of integrity of voltage, of timing, and of signal characteristics in the package, the board, the chip, the pin interface, so that you have a more comprehensive view. And Joules is a new tool which is really stitching this all together to create a unified kind of cockpit, or a way in which all of these different energy perspectives can be combined. There's a lot that's happened in power sign-off, and I won't belabor this because I think this is, you know, standard state-of-the-art stuff in terms of sanity checks, the combination of dynamic and static power analysis, at various stages within the development of a floor plan and the layout of specific blocks, doing the power rail analysis, and also including, you know, the detailed electromigration analysis. But, you know, I think this pair of views of being able to deal with the timing and the voltage together allows people to have a much more unified view of the trade-offs that are at work as you try to have something which meets power goals and meets timing goals. But there are lots of additional challenges. All of this code-dependent and data-dependent power, and the need to find some way to map these high-level scenarios, which want to talk about milliseconds and seconds, down to runs here on which this is done, which are really talking about nanoseconds and picoseconds. There are new kinds of tools coming into play, you know, power-aware debug, power-aware simulation and emulation, low-power formal, where there are formal checks that can be applied in sequential equivalence checking in order to be able to make stronger statements about what the clocked state of the circuit is. And of course, we're pushing hard on these tools like SimVision and Incisive and Jasper and Palladium to do that. And you know, the role of emulation is actually pretty important, and we use it quite routinely within our IP development as a way to get an additional perspective. Even though in the processors we have high-speed simulators and we have all of this power prediction, that everything really keeps coming back to the question of, well, what does it do at the system level? What does it do at the system level? And to be able to build up realistic systems and to run them through Palladium, to put them into FPGA, to put them into all of these real customer-like scenarios, tells us a lot about whether our flow for the individual IP blocks, like the processors, is really giving us the kinds of insights into power that we actually need. I think that there's also a lot of very fundamental challenges as we work to converge the analog and digital flows. So we're doing things like extending the common power format support to really handle the analog designs. And there's a bunch of tools now to allow for this data interchange between a virtuoso analog level view and a digital flow place and route view, so that within the same environment you can do this checking of models. You can construct the necessary models and do simulation in a mixed form. We've recently done some very interesting things of coming up with better ways to do some analog interface, data converters, where we can use very small DSPs for calibration and self-test that allow for really a little bit, I won't say sloppier design, but less aggressively optimized design for the analog portion, which allows it to be more tolerant of process variation, which allows it to move from one process technology to another more easily, by really putting a little offline DSP there that can thoroughly analyze in real time the analog characteristics of the circuit and build in corrections that allow it to be a very sophisticated design on lousy transistors. And that kind of mixed design then drives the need to have these conjoined digital and analog power analysis and power verification flows. So let's take now a look at applications' impact on power and energy. This is a case where we took one particular domain, networking and storage, and say, well, what happens when you optimize at the instruction set level or at the definition of the processor itself? What happens to power? What happens to area? What happens to performance? And ultimately, what happens to energy? And so we looked at a whole suite of different kinds of functions: linked list search and table lookups and compression and hashing and AES. And what we find is that you do have this opportunity to go quite significantly faster. And that translates, if you look at that log vertical scale, into factors of 5 to factors of a few hundred in performance at still some cost, but very low cost in green, in increased area, and therefore increased power per megahertz, offset by dramatic reduction in the number of cycles that it takes to execute, which translates into dramatically reduced energy requirements. So that's one of the tools you have in order to really work on the power problem for these different blocks. Now, this is the case of configurable processors, but I could tell an analogous story about what you can do in different kinds of interface IP or hardwired blocks or memory system components in terms of using a system-level view in order to drive more optimal configuration as the biggest lever on the power issue. But sometimes you have less complete sophistication over around the application in question. But you still, as a designer, are forced to make choices about what you want to put into your processor. And I just took a little screenshot a couple of days ago of our tool here. I'm sorry, it's a little bit hard to read. But this is a menu of choices. And this has choices like how big a multiplier and how deeply pipelined is my multiplier? Do I have floating point? How many registers in my register file? Do I have support for multiprocessor in my instruction set? What kind of total pipeline depth do I have? What are the sizes and types of caches I have? And you click those boxes and you get a real-time feedback here in terms of what is the available megahertz, what is the range of power, what's the range of size for that configuration of the processor. And in particular, even as you move within the target megahertz range or the available megahertz range, you see a good estimate of what the power is on a per megahertz basis for that particular core. And because you have this very big dynamic range, as I said, as much as a couple of orders of magnitude, it's very important to guide that architect through the process of coming up with the right kind of configuration, because overkill on the either overkill or underkill on the application will kill you from a power standpoint. And so getting this kind of instant feedback on power is an essential part of where I think IP is going. There's another tool that we've used internally. So this is not a Cadence tool. This is, or at least this is not a Cadence tool for sale, but this is an example of a tool and methodology that we've developed in order to give our own designers insight into how to get power. So we actually don't do a flattened synthesis, but we do hierarchical synthesis. And then we have a set of tools to extract power on a per subsystem basis within that IP, and then a rapid feedback loop for being able to modify that. And it gives us important choices about, well, what kinds of configuration make sense, or what features should we be considering as part of this IP, and what tell us both microarchitecturally and architecturally where's our time being spent. And again, this is a little bit hard to read from the back row, but we can, from this, look at both absolute power levels from different sources and the distribution of power across different subsystems within the chip, looking at dynamic power, leakage power, looking at cell area. Some of these categories here are the program counter and instruction fetch, the added execution units, the external interface, the load store unit, the baseline 32-bit instruction set features, and the pipeline control units. And you can see that they're well distributed around. This is something where you see some interesting characteristics. For example, over there in the first pie chart, the dynamic power, that for this workload, the added DSP instructions only make up a little over a quarter of the dynamic power, but they make up about half of the leakage power, which says, in fact, that clock gating is working really well, because you don't execute the DSP instructions all the time. So they may consume half the area, and you can see that from the cell area here, and leakage tends to track with the cell area very closely. But the clock gating works extremely well on the DSP instructions, because you don't execute them all the time. On the other hand, the proportion of the power which is consumed by instruction fetch and decode is disproportionately high, because that you do every cycle. You do have to execute that instruction memory and the instruction decode and the instruction buffers all the time. And that particular observation and observations like it have really driven us to make fundamental changes in the nature of the IP and to be able to guide customers to be able to make sensible trade-offs as they work through this configuration space. So now let me change gears again and talk about low voltage. There's this kind of paradox where everyone wants to get to extremely low levels of power. And in theory, at least, our process technologies, our transistors, will take us down in voltage well below where they are typically rated. But the libraries, the commonly available libraries, are really only characterized over relatively narrow voltage ranges. And so you've got all this unutilized potential in lower voltage. And how do you get access to it? And we've taken this by really using some of the tools that operate at the transistor level and apply them to large digital circuits. So for example, we took, this is the design of a rather small tensilica core. It's only a few thousand square microns. And looking at it across a range of 16 and 28 nanometer process technologies and libraries. And did synthesis and place and route optimized at different points, and then looked at the real power, the real leakage, and the real maximum megahertz for that circuit at different voltage levels. But what's real? What can you say is real when you're operating outside the characterization range of the library? And the answer is, heck, I can take the entire netlist with all of its parasitics, throw it into SPICE, and run realistic simulation of a 32-bit microprocessor in SPICE. And it gives me real answers, at least as good as the SPICE deck is now. And moving from SPICE deck level of, or moving from library characterization to SPICE deck characterization gives me one less step of indirection. I get one step closer to what the fab actually is doing. And I get a degree greater confidence that this represents functional reality. And it turns out it indicates that we have some margin here to play with that is extremely useful in getting to extremely low power. So if you look at this, it says that we can get these actually rather powerful processors down into the 1.5 to 2 microwatt per megahertz level. That means, you know, a processor running at a pretty reasonable speed, 100 megahertz, is only dissipating on the order of 100 or 200 microwatts. That's a pretty big step forward in terms of the power you'd expect for these kinds of high-performance systems. It's interesting, as just a little aside, it says actually when you're trying to go for low power at low voltage, it doesn't necessarily mean you want the shortest possible pipeline. In fact, it's helped considerably by the fact that a longer pipeline has fewer gates per cycle. You can afford to have really slow transistors and still get quite reasonable clock frequencies when you have a more balanced pipeline. And we are actually able to use SPICE for functional verification of the digital logic. It's showing that we could run the diagnostics in SPICE up to about 140 megahertz under typical conditions at 0.5 volts in 28 nanometer. I think this is HPM. So pretty reasonable clock frequency for something that's so close to threshold voltage. Mixed signal power, I think, is one of the great remaining challenges. This is something where it's hard to get high quality data across the whole functional space. And it relies increasingly on being able to do a good job on these designs that combine an amazing amount of digital. You sort of think of something like an analog high-speed SerDes PHY as being a real analog trick, and it is. It's got lots and lots of high-speed circuits and PLLs running around, but it also has really a large amount of digital logic in it as well, often running at quite high megahertz. And you've got some of the classic problems associated with lots of power shutoff islands, a need for state retention, isolation between different subdomains, different voltages all mixed together, different testability features mixed with main data path features. And so we've adopted a methodology that, of course, uses pretty much classical, but of course Cadence-centric digital tools, and then feeding into a mixed hardened digital and analog circuit power analysis using some of the new features of Voltus Phi and Cadence, which is Cadence's new features of power sign-off for transistor-level circuits. And this is something which is fully Foundry certified in advanced FinFET nodes and others. And it's helped us a lot in being able to really expand the range of characterization with which we can talk with customers about the power characteristics. Because it's amazing the degree to which power is really catching up now with clock frequency as a key selling characteristics in some of these most advanced circuits like SerDes. People don't want to just know that you can do, 16 or 28 gigabit per second, but they want to know at what power level you're running to do that. Because people want to scale up now with large numbers of lanes, and so the power really matters a lot. So what does it all mean? So I think that we have really recognized that IP is not just about the CV squared F issues. It's really about the system level issues. And the system functionality, as we all know from wondering whether our phone is going to last through the day, system functionality is governed by power and energy characteristics. I would say that we've reached an era in which the complexity of SoCs compels wide use of IP blocks, and it's only going to increase. I think that the chip designers are going to continue to move up in their level of abstraction, which is going to create more and more space for sophisticated individual blocks and subsystem IP that solves significant problems for them, which includes helping to solve their power problems. There are a lot of new tools, and the tools are actually remarkably good. We use them heavily. We use them, we abuse them, we break them. And hopefully our use of those tools is helping to contribute to the quality of the tools as other designers get access to them. We recognize that there's a smooth continuum between the issues for the design of IP to the system level issue of design with IP. IP does make special demands on the tools because of the need for adaptability, configurability, and characterization across these very wide configuration spaces. That is really part of how you make an industrial strength IP work technically for the customer and work financially, that is, serving a large market. There are many different IP approaches for the same function. There are lots of different ways to do any particular kind of compute or data transfer or storage. And you really have to work down from the system requirements to know what trade-offs you're allowed to make in programmability, in generality, in cost, and in energy, and make the whole system come together. And finally, I'd say that there is lots of room for these novel flows of doing things both within the development of the IP and in the use of the tools that gives us some additional leverage over time to keep driving down the energy and power level. Things like taking whole 32-bit processors and doing SPICE simulation on it. Things that allow us to mix analog and digital more freely. And things that allow us to drill down and get visual insight, get detailed information about what's going on in the behavior of the IP as driven from system level activity and what's happening at a low level if you look at the components within one of these subsystems. So there's my contact information, and I'm happy to help out anybody who wants to get some more insight into any of these techniques that we're attempting to do. You know, we don't know everything in the world about power for IP. We have lots that we still need to learn, but we're working very hard on it because so much of our customer base is obsessed, and we are obsessed with them and for them on the power issues. Thank you.
Taking questions?
Sure. I mean, that's up to the organizers as to whether or not I have time.
Okay.
Oh, what was that, Dennis?
Are you allowing questions? That was one question.
Next question.
I think we're a little bit behind, but I think it's worth it.
All right, I didn't.
You got 2 more wishes.
Yeah.
We'll just start the reception a little bit later.
It's a quick one. If you're trying to vary the voltage on your CPUs with like DVFS, how are you verifying that? I don't think you can do that in emulators, and SPICE seems rather a long way to do it.
You know, I think ultimately what it really means is that you go to much more fluid recharacterization of the libraries with things like Liberate. And you have a smoother continuum of voltage points that you support. But you do have to go through the characterization of the, but not necessarily the re-optimization of the circuit across the whole voltage range, so you know what are the interesting allowable voltage and frequency combinations for it. And then you get to play the DVFS game of deciding how often you want to switch, which is really a function of what's the overhead for switching versus the incremental energy savings that you get from switching down by, 1 detent in time, 1 detent in voltage. So, in practice, people tend to work towards having only a very small number of voltage points at which they operate. And the mechanisms at work in terms of making decisions about when I want to operate at what voltage are today crude and very system level. The system has to make a guess about what's coming next. It's often at the level of operating system behavior or expected behavior on a user interface. And so the time granularity actually turns out to often be fairly large for these switchings between voltages. Very rarely can you say, yes, I know that I don't have very much work to do for the next 100 microseconds, and I can run at this lower frequency and voltage combination. So it tends to be, I think, still today often rather granular. But I think the mechanisms are there to be able to support it. It's more limited by the patience and the know-how at the system level to decide, what is my future load going to be? Dennis.
I'll ask my second question. Your early slides motivated us that we're in the IP era,
Yeah.
and that as we go to smaller geometries, it's obvious that we are in an IP era. And yet, our first speaker today, the keynote, Dan Armburst, was giving out data showing that majority of the silicon coming out is not even at the 65 nanometer node that I think was the largest geometry you had on your slide, but maybe 130 is actually even more popular. And I'm just wondering, is the IP world that you're showing at these lower nodes, is that a fact? Is that an artifact of it being so new? And that over time, the need for IP and creating systems that way will go away? Or is it just the quickest way to fill up more available silicon real estate, that maybe silicon becomes more free? And therefore, why not just put anything and everything on your chip?
Yeah. Well, two parts of an answer. First, I think when you look at the statistics, you have to look very carefully at the question, are you looking at production statistics or are you looking at design statistics?
I had a hard time ferreting
Yeah.
out that from what I've seen so far.
Yeah. And certainly today, what we're producing is several years behind relative to what we're designing. But if you look at the complexity weighted volume of designs, it's pretty clear that an awful lot of the design on a per gate basis is taking place on fairly advanced nodes. And we would expect to see that continue to migrate forward, such that by 2020, almost half of the volume we expect to see is at, is below 28 nanometer.
New node after 2020, when we reach 5, are we going lower?
I've been in conversations worrying about the end of Moore's law. Since, as I recall, it was 1982, and I was working at Intel, and we were worrying about the end of Moore's law. And so I'm not saying that they're wrong yet again, but it does seem likely that people will continue to invest and continue to find clever, implausible ways to give us more density than before, and that there will be meaningful benefits of some sort in capacity or density, and maybe a bit in power, maybe a bit in speed of moving forward. It isn't going to be on the old curve, but it still is going to pay for new capital investment, and there will be new nodes to design. I think more importantly, we've already reached an era where the phenomenal density is so great that there are, billions of hypothetical designs that we could do on the current nodes that we can't do yet because we just don't have enough design capacity. We don't have enough automation or enough designers to do all these interesting chips. And so it could very well be that we see a significant slowdown in the rate of progress on the traditional silicon scaling characteristics without a slowdown in silicon design. Because I don't think we necessarily have to go to, 3 nanometer in order to do something interesting. That there are a gazillion designs that we'll be able to do at 16 for a long time to come. Yeah, sure, if your design just blindly depends on the next doubling of the amount of on-chip RAM or the doubling of the number of cores you put on, yeah, that's going to slow down. But the level of creativity, particularly driven from system know-how, rather than just saying, oh, last year's chip times 2x, I think is very great. And so I'm an optimist on the question of design creativity and design activity because of this really untapped potential in even the current processes.
I think we got to call it.
Oh, okay,
All right.
sure.